All right, let's start 6.2. Go ahead and pause me and copy what you see on your screen. Okay, so the review at the top is from Algebra 1 when we're multiplying underneath the radical. So remember that even though there's no multiplication symbol there, it's implied. There is a times b. We can separate that into two radicals that are being multiplied, okay? Now, that goes both ways. I can separate it from being one radical into two radicals, but I can also smush it from being two radicals into being one radical. So that's what I'm going to do with this first example. There's nothing I can do to simplify the square root of 6, but there is something I can do to simplify the square root of 12. So first thing I'm doing is smushing them together under one radical and multiplying the 6 times 2. And then we need to go back to Algebra 1 again and think about what perfect square goes into 12. So you might want to list at the top your perfect squares, or maybe you are really good at this and you don't need that. So from that list, 4 goes in. So we're going to split this into 4 times 3. And then you may not show this step, but we can break it up. Just like we smushed it together, we can break it up. So we can go back and forth. Now, the reason that it feels like we're going in a circle, but we're really not, because I can simplify the 4. I know the square root of 4 is 2, but I don't know the square root of 3, so I'm going to leave that alone. So this is my answer. Now, if you look back up at the top, there was nothing I could do to the 6 or the 2, so I had to smush it back together so that let me start over. I had to smush it together so that I could pull it back apart in a different way so that there was a perfect square. Okay? The same thing is true for cube roots. I can smush these together, so I'm multiplying the -4 times the 2, and then I want to think the cube root of -8. So we talked about this last time. Is there a number times itself that equals -8? And the answer is yes, -2. And if you want to check it, do that multiplication in your head, okay? So -2 times -2 times -2 is a way to check that answer. Now this one, notice these ones were the same root. This had a square root, an invisible 2 there. These both had a cube roots, right, in part B. But there's a cube root and a square root, so we can't simplify. The root index has to be the same, okay? So that one we can't simplify. Now looking at D, there's no multiplication going on, so I'm going to jump straight to the simplifying step. I want to know, is there a perfect cube that goes into 128? So I really highly recommend that you make a list of perfect cubes as you're doing these problems. So 1 cubed, 2 cubed, 3 cubed, 4 cubed, and we'll see if we need more. I'm going to leave it at that for a minute. We'll see if we need more for either D or E, because those are both perfect, or those are both cube roots. So I stopped at 64 because I was looking at that 128 as I was writing the list. 1 doesn't do me any good. 8 doesn't go into 128, 27 doesn't go into 128, but 64 does. So I'm going to break this up into the cube root of 64 times the cube root of 2. 64 times 2 makes 128. And then I need to think about the x to the 7th. Whoop. Just drew a random line. Try that again. The x to the 7th, I'm going to break up into a perfect cube, which is x to the 6th, and whatever's left. So I'm looking for an exponent that's a multiple of 3. So the largest multiple of 3 that goes into 7 is 6. So I broke it up into x to the 6th and x to the 1st. So then now I need to ask myself, well, we already figured it out, right? We said this was 1 cubed, this was 2 cubed, this was 3 cubed, and this was 4 cubed. So the cube root of 64 is 4. And then the cube root of x to the 6th is x squared, and I'll show you why in just a second. And then I can't do anything, let me color code this for you. I can't do anything with these, so they have to stay under the cube root. So this is my answer. let me show you why the cube root of x to the 6th is x squared. X squared times x squared times x squared equals x to the 6th. So the cube root is going to be x squared because we're looking for something times itself, right? All right, so let's do it again. 54. So the question is, does something from this list, now I'm going to put a dot, dot, dot because the answer is yes. Does something from this list go evenly into 54? Okay, they wouldn't give us this problem if there wasn't a perfect cube that didn't go in. So 27 goes in evenly. So I'm going to break up the 54. 27 times 2. And then I want to think about the x to the 5th. So the highest multiple of 3 is x to the 3rd. Whoops, I did not write x to the 3rd. So that means I have 2 of them left because x squared times x to the 5th is x squared times x to the 3rd is x to the 5th. And then we already said over here that 27 is 3 cubed, so this is going to come out as a 3. The cube root of x cubed, we know the cube root and the exponent are going to cancel out, so we're just left with x. And then again, these things I can't do anything with. So I'm going to have 2x squared that is stuck under the cube root. Alright, let's do another one. Now, this one looks pretty gross. We need to think about what we're doing before. There's different ways to do different problems. So if we look up at the top, A, B, and not C, we multiplied these together and broke them apart, and that was a pretty easy way to do these two problems. Multiplying 6 times 2 is 12. Over here, 45 times 35, I don't want to do that. Okay, I really don't want to do that. So I'm going to think about simplifying these before I multiply them together. So these are square roots, so I'm looking for a perfect square. So 9 is a perfect square that goes into 45. And then since it's a square root, I'm looking for multiples of 2. So I'm going to break, here, let me color code this again. The x to the 5th is going to become x to the 4th times x. The y to the 3rd is going to become y squared times y. And then let's see, do I have some space? There we go. 35, there's no perfect square that goes into 35. 35 is just equal to 5 times 7. Those are prime numbers, and neither of them are perfect squares. So I'm going to leave that alone for now. And then there's x is just x. There's nothing I can do with that. And then y to the 4th, 4 is already a multiple of 2. So I've got a bunch of stuff going on here. Let's see what we can simplify. Let me find a different color. How about that? Okay, I can take the square root of 9. I can't take the square root of 5. I need a calculator for that. I can take the square root of x to the 4th. Square root of x is just square root of x. I can take the square root of y squared. I don't know the square root of y. I don't know the square root of 35. I don't know the square root of x, but I do know the square root of y to the 4th. So these are all being multiplied together. And then we can write what we have left. So we've got a 5 that's not underlined in that purpley pink color. We've got a 35 that's not underlined in that purpley pink color. And then I have an x and a y and an x. So just scroll through and make sure we got everything. And we did. So this is 3x squared y to the 3rd. Remember, reviewing properties of exponents, we add the exponents, 1 plus 2 on the y. Now, we've got a little bit more work to do. So this is the hardest example, okay? 35 has a factor of 5. So we need to recognize that if we break the 35, up like this, we'll be able to simplify, okay? And then we've got x squared y. Remember, we're looking for something times itself, and if that happens, we can take it out of the square root. Oh, that's a different color at the end, isn't it? I didn't mean to do that. If that happens, we can take it out of the square root. So I have something times itself right here. 5 times 5. I can take that out as a 5. The square root of 5 times 5, or 25, is 5. I can also take out, this is something times itself, x squared, so I can take that out as an x. And then everything else I'm going to keep the same. I have 3x squared y to the third in front of that, and then I didn't do anything with the 7 or the y under the radical. So last thing, just multiplying these together. Okay, so remember adding the exponent on the x squared, and x to the first. Ooh, that's a long one, right? Okay, so let's go, getting a little smushy in my notes here. Let's go to this review right here. So that's also Algebra 1. Actually, all of this is Algebra 1. I can split up radicals with division just like I can with multiplication. I cannot do it with addition or subtraction, so don't start doing that, okay? And just like I can split them up, I can smush them together. So I can write this as all one radical, so that then I can divide. So I'm going to divide 50 by 2, and I'm going to get 25. I'm going to divide x to the fourth and x squared, and remember from last time, when we divide with exponents, we subtract, okay? And then now I know the square root of both of those. The square root of 25 is 5, and the square root of x squared is x. Nice and simple. Now, I want you to think about b for a second. What do you notice? All right, so hopefully you said they're not like radicals, so we can't simplify. So let's do c. We can put them under the same cube root, and then we can divide. So I got to think about 3 goes into 16, that's 5, right? 15 with 1 left over, so 12, so 54. Dividing, I wanted to color code this for you again. Dividing the 162 by 3 gives us 54. And dividing the y to the fifth and the y squared gives us y to the third. And be careful not to lose your radical. Okay, we have a cube root here. And then, didn't we already do a cube root of 54? We broke it up into 27 and 2, right? So we're going to go cube root of 27, cube root of 2, cube root of y to the third. And if you look at the previous example, we said the cube root of 27 was 3. And remember that a cube root and an exponent of 3 cancel each other out. So we have just y there. And then I need a calculator to evaluate the cube root of 2. All right, last thing, algebra review again. I may not be able to finish these because I'm limited to 15 minutes. So I'm going to start with C, because that's the only new thing. So I need perfect cubes under the radical to get rid of the radical. So that means I need to multiply by 3 squared and x squared on top and bottom. I'm trying to get the radical out of the bottom. So the reason for that is, watch what happens in the bottom. When I multiply those together, I end up with that. And then the top is going to be, I've got a 5 times 9. So now I can take everything out of the bottom, okay? And then we just need to check if 45 can be split up into any kind of perfect cubes from our list, and leave it at that.